In this video, we're going to define 6 trigonometric functions using a right triangle. And then we're going to learn how to use these trig functions to answer some different problems. So first, let's go ahead and define all of our trig functions using a right triangle. So here's my right triangle. I'm going to call this angle theta, and we're going to define all of the trig functions of this particular angle. This side over here, I'm going to call the opposite side, because it's opposite my angle. This side is the adjacent side, because it's adjacent to our angle. And then the diagonal side, that's our hypotenuse, taken from the name of that particular side of a right triangle. So our first trig function is called sine. And the sine function is denoted by sine of theta. So a trig function has an input of an angle. And sine of theta is equal to the opposite side of the triangle divided by the hypotenuse of the triangle. Our next trig function is cosine, which is abbreviated just COS of theta. And it is calculated as the ratio of the adjacent side over the hypotenuse. And then we have our tangent function. Tangent of theta is the opposite side over the adjacent side. So all of our trig functions are going to be defined as ratios of sides of a right triangle. Sine's opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent's opposite over adjacent. And these three trig functions are often remembered using SOHCAHTOA, where S is for sine, opposite hypotenuse, C for cosine, adjacent hypotenuse, T for tangent, opposite adjacent. Doesn't matter how you memorize these, as long as you get them memorized. So those are our first 3 trig functions. They're the ones people are usually the most familiar with, but we have 3 others to learn about as well. We have our cosecant, which is abbreviated CSC of theta, and cosecant is hypotenuse over the opposite. Then we have secant, which is just SEC of theta. That is the hypotenuse over the adjacent. And then we have our cotangent, which is COT of theta. That is our adjacent over the opposite. These 3 people tend to not memorize as much with this particular definition. Rather, they tend to memorize these using various relations among the trig functions, which we will get to later in this video. So let's do an example using these 6 trigonometric functions and a right triangle. So example. Suppose that right triangle ABC has legs of length 6 centimeters and 3 centimeters. Evaluate the 6 trig functions for angle B, which will be the larger acute angle. Well, in order to figure this out, we're going to have to actually draw our triangle first. When we have this triangle drawn, we'll be able to see what the measures of all the sides are, and then it's just a matter of using those ratios of sides to find all of our trig functions. So let's go ahead and just draw what this right triangle looks like. So here's a right triangle. And I know that my sides are going to be 3 centimeters and 6 centimeters. And it says angle B is going to be the larger acute angle, which is kind of hard to tell in my drawing, but I know that the larger angle is going to be opposite my larger side. So there's angle B. Now I have the adjacent side is 3, the opposite side is 6. I still need to find the hypotenuse because I'm going to need that for some of my trig functions. How do we find the hypotenuse? That's where the Pythagorean theorem comes in. So by the Pythagorean theorem, I know 3 squared plus 6 squared is equal to my hypotenuse squared, and I'm going to call that C. So I have 9 plus 36 is C squared, and that gives me 45 is C squared. If I take the square root of 45 and simplify it, I get 3 times the square root of 5 is C. So my hypotenuse is 3 square root 5. And now I'm ready to find all of my trig functions of angle B. Let's start with sine. Sine of B is the opposite over the hypotenuse. My opposite side is 6. My hypotenuse is 3 times the square root of 5. If I simplify this, I have 2 over the square root of 5. Now, some books and homework systems might require you to rationalize the denominator so that you don't have a square root in the bottom. Really, that should depend on your particular instructor. I personally don't mind having square roots in the bottom, but depending on the homework system, you might need to rationalize it. So I would say that the answer is sine of B is 2 over square root of 5. But if you rationalize the denominator, you would multiply the top and the bottom by square root 5, and you get 2 square root 5 over 5. Either of those answers is acceptable. I'm not going to bother rationalizing all the other ones, but remember, if you need to rationalize the denominator, you just multiply the numerator and the denominator by that square root and simplify. All right, so we got our sine. Let's do cosine. Cosine of B is adjacent over hypotenuse. So that's 3 over 3 square root 5, which if I simplify that, I get 1 over the square root of 5. So I have my sine and I have my cosine. I still need to find tangent, cosecant, secant, and cotangent. Let's put our tangent over here. Tangent of B is opposite over adjacent. So I have 6 over 3, and that simplifies to 2. Now let's try our cosecant. Cosecant of B, remember your cosecant is equal to hypotenuse over the opposite. So I have my hypotenuse is 3 square root 5, opposite is 6. And so when I simplify, I get cosecant of B is equal to the square root of 5 divided by 2. Notice that it's the same thing as our sine of B, just the reciprocal. It's flipped upside down. We'll come back to that a little bit later in this video. Now let's try secant. Secant of B is equal to the hypotenuse over the adjacent, which when I simplify, I get square root of 5. That is the same thing as our cosine, but the reciprocal. So it's our cosine upside down. Last one to check is our cotangent. Cotangent of B is adjacent over opposite, 3 over 6. That means cotangent of B is 1/2, which is the reciprocal of our tangent of B. Now the question is that always going to happen, or is it just this particular triangle that we got this reciprocal relationship? And stay tuned in this video, we will find out if this is always true or not. All right, so we found all 6 trig functions just by using a right triangle and looking at ratios of sides of the triangle. It's not too bad as long as you remember your definitions, which side goes where in the definitions of these functions. Let's do another example. Let's suppose that sine of theta is equal to 3/4. And then we need to evaluate secant of theta. Well, what I would do on this is draw a triangle to organize my information. Here's my triangle, and I'll put theta down here. I know sine of theta is 3 over 4. And I also know that sine is equal to the opposite over the hypotenuse. So the opposite side is going to be 3, and the hypotenuse is going to be 4. Now, my secant is equal to hypotenuse over adjacent. So I need to find this adjacent side in order to find my secant. So let's find that side. Let's call it x for now. Using my Pythagorean theorem, 3 squared plus x squared equals 4 squared. So 9 plus x squared is 16. X squared equals 7. That means x equals the square root of 7. And now I'm ready to use my definition of secant. Secant of theta is equal to the hypotenuse over the adjacent. So 4 over the square root of 7. And again, that could be written differently if you rationalize your denominator. All right, so that is how we use our definitions from right triangle trig to evaluate different trig functions. Now let's talk about the trig values for some very particular angles, some very special angle measurements. So trig values of special angles. All of the trig values in this chart I'm about to write down can be found by using the special right triangles that you learned in geometry class. Your 45, 45, 90 triangles and your 30, 60, 90 triangles. So we're going to have our theta. I need a little more room than that. Let's look at sine of theta, cosine of theta, and tangent theta. And I'll have to make a separate chart for the other trig functions, so I don't have enough room to fit it all the way across. So our first special angle is when theta is 30 degrees, which is the same thing as pi over 6 radians. If our theta is pi over 6 radians, or 30 degrees, then sine of theta ends up being 1/2. Cosine of theta is square root 2 over 2. And tangent theta is square root 3 over 3. if my angle is 45 degrees, which is pi over 4 in radians, my sine of theta, oh, I made a mistake here, I'm sorry. My cosine theta, when theta is 30 degrees, is square root 3 over 2, not square root 2 over 2. So I have sine of 30 degrees is 1/2, cosine of 30 degrees is square root 3 over 2, and the tangent of 30 degrees is square root 3 over 3. Now, if I'm going to find all of these trig values at 45 degrees, which is pi over 4, my sine is square root 2 over 2, my cosine is the same thing, and my tangent is 1. My last special angle is 60 degrees, which is pi over 3. I get square root 3 over 2 for my sine, 1 over 2 for cosine, and square root 3 for tangent. Now I'm going to fill in the chart for the other 3 trig functions as well. I strongly suggest that you memorize at least the sine and the cosine. When we get through the end of this video, we'll have all sorts of relations with the other trig functions, that as long as you have sine and cosine memorized, you can derive all of the other trig values of these special angles. So now, let's see what happens with our other trig functions. We're going to have the same angles, but now we're going to use our cosecant, our secant, and our cotangent. At 30 degrees, or pi over 6, your cosecant of theta is 2. Your secant of theta is 2 square root 3 over 3, and your cotangent is square root 3. At pi over 4, cosecant is square root 2, secant is square root 2, and cotangent is 1. And at pi over 3, my cosecant is 2 square root 3 over 3, my secant is 2, and my cotangent is square root 3 over 3. Now, in this chart and the previous one, I'm sure you noticed some patterns. Like, I have at 45 degrees, my sine and my cosine were equal, but also my cosecant and secant are equal. And I also have this little opposite relationship in my chart. Down here, I have 2 square root 3 over 3. I have the same value up here. And same with these 2's. And that same sort of pattern was happening with the sines and cosines. And again, as long as you have the sine and cosine values memorized for these special angles, you will be able to derive all these other ones after we learn the relations between all of the trig functions. Now, let's just do an example simplifying a statement that uses trig values of special angles, and we can simplify using our chart. So simplify sine of pi over 3, cosine of pi over 6, plus cosine of pi over 3, sine of pi over 6. Well, using my chart that we had, sine of pi over 3 is square root of 3 over 2. Cosine of pi over 6 is also square root 3 over 2. Cosine of pi over 3 is 1/2. Sine of pi over 6 is also 1/2. So when I multiply these things together, I get a 3 over 4 plus a 1 over 4, and I get 1 for my simplified answer. So this is just a super fancy way of writing 1. All right, now we're going to learn some of the relationships between our trig functions so that it'll be a little easier to work with them and a lot less memorization. When you learn how all the functions are related together, you don't have to memorize quite as much. So these are the reciprocal and quotient identities. The first one says cosecant of theta is 1 over sine theta. And sine of theta is 1 over cosecant of theta. What this is saying here is that sine and cosecant are reciprocals of each other. So when we observe that with our first example, that actually happens with all right triangles. It's not just for that particular right triangle. So if I know the sine of theta, I can find the cosecant of theta by flipping my sign upside down. Another identity is the same thing except with secant and cosine. So secant is 1 over cosine, and cosine is 1 over secant. They are also reciprocal functions. Our last reciprocal identity is that cotangent of theta is 1 over tangent, and tangent of theta is 1 over cotangent. So tangent and cotangent are also reciprocal functions. If you know the value of one of them, you can find the value of the other one by just flipping the answer upside down. So those are the reciprocal identities. And now the quotient identities relate both tangent and cotangent to our sine and cosine. Tangent of theta is equal to sine of theta divided by cosine of theta. And cotangent of theta, remember cotangent and tangent are reciprocals of each other. So this means cotangent of theta is cosine over sine. So that's why we only really need to memorize the sine and cosine values for those special angles, because I can find all of the other ones using these identities that we just wrote down. Let's do an example using these identities. Given that sine of beta is 3/7 and cosine of beta is 2 square root of 10 over 7, find the other trig functions of beta. And I'm going to use those identities we just learned. So I have sine and I have cosine. Using some of my reciprocal identities, well, I know that my cosecant of beta is going to be 1 over sine of beta. I get to flip my sign upside down. So cosecant of beta is 1 over sine beta. That means I'm going to get 7 over 3. I'm doing the same thing with my secant beta. Secant is 1 over cosine. So I can flip my cosine upside down and get 7 over 2 square root 10. So I have cosecant and I have secant. Let's go ahead and find tangent using one of those quotient identities. And then we can find cotangent from that. So tangent beta is equal to sine of beta over cosine beta. So if I plug in the values for sine and cosine, I have 3/7 over 2 square root 10 over 7. And remember, dividing by a fraction is the same thing as multiplying by the reciprocal. My 7s will cancel out, and I'll get 3 over 2 square root 10. Then, using one more reciprocal identity, cotangent beta is supposed to be 1 over tangent beta. So I can flip my tangent upside down and get my cotangent to beta as 2 square root 10 divided by 3. And so we were able to find all of the other trig functions without even drawing a triangle this time. We were able to just use these identities and the relationships between the trig functions. Now we're going to learn even more relationships between our trig functions. We're going to learn the Pythagorean identities. And I'm going to show you where one of them comes from. So let's take a look at a right triangle. A, B, and C, and here's my theta. So from this right triangle, with A, B, and C for the sides, we know that A squared plus B squared is C squared. That's my Pythagorean theorem. Now I'm going to divide both sides of the equation by C squared. So I get A squared over C squared plus B squared over C squared is equal to 1. And then I can write this as A over C squared plus B over C squared equals 1. But now looking at my triangle, what is A over C? That is opposite over hypotenuse. That's sine. B over C is adjacent over hypotenuse. That's cosine. So this is saying sine squared plus cosine squared is equal to 1. And the way we write sine squared, we generally put the squared right next to the sin and not on the outside. Sine squared theta plus cosine squared theta is equal to 1. That is one of our Pythagorean identities. But now you see where it comes from. We have two other Pythagorean identities that can be found also using a right triangle and the Pythagorean theorem. And so we have 3 of these. Pythagorean identities. We have the one we just discovered, sine squared theta plus cosine squared theta is equal to 1. We also have tangent squared theta plus 1 equals secant squared theta. We can actually get that particular Pythagorean identity by using the one we had already discovered in dividing everything by cosine squared. And my last one that I have is 1 plus cotangent squared theta is equal to cosecant squared of theta. All 3 of these are my Pythagorean identities, and they are based off of the Pythagorean theorem. These are very important to know because they come in very, very handy when you're doing a lot of problems in calculus. Let's do an example. Given that cosecant of theta is 5 over 4, use a Pythagorean identity to find cotangent of theta. So I want to use one of those Pythagorean identities to find cotangent. Now, Which one should I use? Well, we should use the one that has a cotangent in it. My Pythagorean identity said 1 plus cotangent squared theta is equal to cosecant squared of theta. Now I know what cosecant of theta is, so let me plug that in. Cosecant of theta is 5/4, so I just need to square that. I have 1 plus cotangent squared theta is equal to 25/16. Now I'm going to solve this equation for cotangent of theta. We're going to subtract 1 from both sides and then take a square root. When I subtract 1, I get the cotangent squared of theta is equal to 25/16 minus 1, which is 9/16. And then I can just take a square root of both sides and simplify my square root to get cotangent of theta is equal to 3/4. And so we used just the Pythagorean identity and our given information about cosecant, and we were able to find cotangent without drawing a triangle out. So I'm sure you can see these identities can be pretty handy. They're not too bad to work with, and it helps us solve for different things without drawing a whole triangle every single time. There are tons of different trigonometric identities that we're going to be learning about throughout the course of these videos. The next ones we're going to learn are called cofunction identities. And the cofunction identities just basically say cofunctions of complementary angles are equal. Now, what do we mean by cofunctions? Well, sine and cosine are cofunctions. Secant and cosecant are cofunctions, and tangent and cotangent are cofunctions. So you can tell which ones are cofunctions just based on their names. Now we have to remember what are complementary angles. Complementary angles are angles that add up to 90 degrees. And remember also 90 degrees is pi/2. So sine of theta is going to be equal to cosine of 90 degrees minus theta. And that is the same thing as cosine of pi/2 minus theta. Similarly, cosine of theta is sine of 90 degrees minus theta, which is sine of pi/2 minus theta. These are the same types of relationships that we're going to have with secant and cosecant, and tangent and cotangent. So let me just write those ones down. Secant of theta is cosecant of 90 degrees minus theta, which is cosecant of pi/2 minus theta. Just depends on whether you're using radians or degrees. Similarly, my cosecant of theta is secant of 90 degrees minus theta, which is secant of pi/2 minus theta. And just so that we have it all complete, we'll write down the cofunction identities for tangent and cotangent. Tangent of theta is cotangent 90 degrees minus theta, which is cotangent of pi/2 minus theta. And cotangent of theta is tangent of 90 degrees minus theta, which is tangent of pi over 2 minus theta. So that's all of our cofunction identities. And it looks pretty scary, but it really isn't that bad. This is just saying if you have complementary angles, your cofunctions are going to be equal. Let's do an example using these identities. So find a cofunction with the same value. So we're given tangent of 22.5 degrees. And we want to find a cofunction that will have the same value as this. Well, using my cofunction identities, I know that tangent of an angle is equal to cotangent of 90 degrees minus that angle. So this is cotangent of 90 degrees minus 22.5 degrees, which is 67.5 degrees. And if you wanted to check this, you could type it into your calculator. Tangent of 22.5 degrees and cotangent of 67.5 degrees will get you the same answer. Let's do one more of these, but with radians. Secant of pi over 3. Well, using my cofunction identities, I know secant of pi over 3 is equal to cosecant of pi over 2 minus that angle. So I have cosecant of pi over 2 minus pi over 3. I would need a common denominator of 6 in order to do that. This guy is going to be 3 pi over 6, and this one's 2 pi over 6. So I just get cosecant pi over 6. And again, you could type those into your calculator and verify you get the same value. In this case, you get a very nice value of 2. The other example, you'd get kind of a messy decimal if you typed it in. All right, well, we have just one more example for this video. We're going to try to do a more complicated word problem just using our right triangle trigonometry. So let's suppose that a farm worker determines that the distance along the ground from her position to the base of a palm tree is 16 feet. And then she measures the angle of elevation from an eye level of 5 feet to the top of the tree as 45.9 degrees. Is the tree tall enough to harvest? if it must be at least 20 feet tall to harvest. So I had to erase the very beginning of the problem, but this is just saying that the distance from the feet of our particular farm worker to the base of this tree is going to be 16 feet. Then we have an angle of elevation from her eyes to the top of the tree as being 45.9 degrees, and her eyes are 5 feet above the ground. We want to figure out how tall the tree is using this information. And I would suggest that we draw a picture, and then we can use our right triangle trigonometry. So if this is the ground, I have my worker right here, and I have my palm tree over here. What a beautiful picture, right? So I have the distance on the ground to the base of the palm tree is 16 feet. And then we're talking about the angle of elevation from the eye side. So first, notice that this distance from the eyes to the tree is also 16 feet. The angle of elevation, we're talking about the angle formed going from the eyes to the top of the tree. And this angle of elevation is 45.9 degrees. And I know that the eyes are supposed to be 5 feet tall. So this is 5 feet over here. Notice that that means this distance here is also 5 feet. I want to know how tall the tree is altogether. Well, the tree is going to be 5 feet plus whatever this height is, which I'm going to call x. So let's figure out what x is first. Notice that we have a right triangle here. I have an angle of 45.9. I know the adjacent side is 16. The opposite side is my x. So I know that tangent of 45.9 is equal to x over 16. And I can solve this for x by just multiplying by 16. Now, we can't get an exact value for the tangent of 45.9 degrees, but we can type it into our calculator and see what we get. So 16 times tangent of 45.9 degrees, this is approximately equal to 16.51. So I know x is 16.51, and that means the tree is 16.51 feet plus 5 feet. So the tree is 16.51 feet plus 5 feet, which is approximately 21.51 feet. And I'm only saying approximately because our 16.51 is an estimate. Now, the question was, is the tree tall enough to harvest? And the tree has to be at least 20 feet tall to harvest. And yes, it is. The tree is about 21.51 feet tall. So yes, the tree is tall enough. And so we were able to determine that this tree was tall enough for harvest just by using our right triangle trigonometry. And that's all I have for you on this particular video. If you have any questions, you can feel free to drop them down below and I'll get back to them as quickly as I can. If you're a current student of mine, you can also ask me questions through email or office hours. And I will see you guys next time.